Welcome back. In this lesson, we are now going to apply eigenvalue dominance to looking at models, and specifically we'll take a look at these models called stage matrix models. And a stage matrix model is similar to a Markov chain. And what's a Markov chain? Well, that's the formal name for a closed transition model where 100% of the starting populations are there after each unit of time, i.e. no overall growth or decay of the population. So when we think back to our rural and urban example, that is one where we had a Markov chain. But for a stage matrix model, we allow the possibility that the system is not closed and that there may not necessarily be a steady state population. So for example, consider birth-death processes. So populations either grow over a long period of time or die off after a long period of time, depending on the birth-death trade-off. So we'll take a look at a couple of examples. We'll build a model, we'll analyze the model, we'll produce eigenvalues and eigenvectors, and make arguments about long-run behavior. So consider a population of magical elves that has two groups, infants and adults. And so now we already can think about this as adults can't become infants. So the travel from one state to the other can only go from infants to adults, in the sense that infants can become adults, but adults cannot become infants. Infants cannot perform magical spells yet, but adults can. We let time be in increments of 5 years. In other words, when we're talking about t equals 1, that's actually going to be 5 years later. T equals 2 will be 10 years later. For the first 5 years, an elf is considered to be an infant. 93% of all elves survive to become adults. The remaining 7% do not survive. So already we're going to get a reduction in the population size just from the survival rates. 75% of all adult elves survive each year, which means that the 25% don't. And thus those 75% will remain as adults in the next time unit. Each adult gives birth to, on average, 2 infant elves. So we can see that we also have a birth cycle. So I'm going to draw a state transition matrix for this, and it's going to look very similar to our previous models, except we're now not going to have 100% survival rate. So we'll have infants, which I'll just call I, and then we'll have adults, which we'll call A. Those are our two states. Now we know that 93% of infants survive to become adults. So that means, I'm going to write it like this. I at time n plus 1 will be, first of all, 93% of the infants at time n will become adults at time n plus 1. And then 75% of the adults survive, so we'll write an arrow here and we'll say that 75% of the adults at time n become adults at time n plus 1, or that is, they remain adults. Now the 7%, we don't really need to worry about this, but I'll draw a 7% of I sub n, and those simply exit the system, because those are the elves that do not survive, so they're no longer part of our cycle. And similarly here, if 75% survive, that means 25% of adults at time n leave this cycle. So we don't need to worry about those 25%. We just need to worry about the 75% that remain in our system. Now we have one other little hitch, and that is that each adult gives birth to, on average, 2 infant elves. So that means that the number of adults at time n, if there were, for example, 100 adults, then each of those is going to, we're assume, gives birth to 2 infant elves. So we can actually, that's going to be 200 new infants that are going to be born, because we have 2 infants per 1 adult. And if we multiply that 2 by the number of adults that we have, that's going to give us, look at the units, 200 infants at time n plus 1. So basically, to get the number of infants at time n plus 1, we need to take 2, which is infants per adult, multiply it by the number of adults. That's going to give us the number of new infants. So this 2 is not a percentage, although you could think about it, I guess, that way, but it really has units of infants per adult. This 0.93 is a percentage. It's a proportion of IN, as is this 0.75 AN. It's a proportion of that AN. So now we're ready to build a recursive system of equations for this model. And so we're going to write two. We're going to write I at time n plus 1. And we've already set this up. That's going to equal, first of all, 0% of the infants at time n will become infants at time n plus 1. Because remember, every iteration of time, that's 5 years, passes. So infants can only become adults, but infants cannot remain infants. And then also the number of infants at time n plus 1 is going to be 2 infants for every adult at time n. And the adults at time n plus 1, well, that's going to be 93% of the infants at time n, plus it's going to be the adults that survive, which is 75% of the adults at time n. And so now we have our system, and we can proceed to create a matrix equation out of this. And so by this time, we are now familiar with this process. We have that, we'll call this vector here that we have, we'll call that x sub t plus 1. And that's just the state of infants and adults at time. Oh, sorry, I won't use t plus 1, I'll use n plus 1 to stick with our convention. And we see that that's going to equal, well, our transition matrix is going to be 0, 2, 0.93, and 0.75 times the number of infants and adults, so I sub n, a sub n. And so really what that becomes is x sub n plus 1 equals our A matrix multiplied by the states at time n, the state vector at time n. So this looks very similar in nature to what we've already done in lessons previous. So now we're going to convert this system of recursive equations into a system that gives the number of elves at some future time t based only on the number at time t equals 0. And we already know that that's going to be that x sub t we can find by taking our transition matrix to the t power multiplied by our initial state. Now, we could figure out what's going to happen in the long run, and in our next part of this problem, we want to find the eigenvalues and eigenvectors by using appropriate technology. So here's how to do it in Wolfram Alpha. Use the diagonalization vector decomposition theorem to provide equations for each of the two groups, infants and adults, as a function of t. Suppose there are initially 20 infants and 30 adults. So the first thing we need to do with this decomposition theorem is we've said that as long as we get linearly independent eigenvectors, and this is a 2x2 system, that we could write this as k1, some scalar multiple of v1, added tip to tail to some scalar multiple of v2. Now x naught is our infant adult vector at time 0, which is 20 and 30, given to us here and here. And that's going to equal some multiple of v1. So I've already computed the eigenvectors here using Wolfram Alpha, and we're just going to go ahead and round these to do 2 decimal places. That's sufficient. So we see v1 is 1.12 and 1 plus k2 times v2, and v2 is negative 1.92 and 1. And so now to solve this system, I'm going to convert it to a Gaussian form. So 1.12, 1, those are the coefficients of k1. The coefficients of k2 are negative 1.92 and 1. And then we want that to equal constants 20 and 30. Now when I performed Gaussian elimination on this using technology, we come up with the matrix 1, 0, 25.53 or thereabout, and 0, 1, 4.47. And so what that tells us is that K1 equals 25.53 and K2 equals 4.47. Now we could just check our work to make sure that if I take 25.53 times 1.12 plus 4.47 times negative 1.92, that I get about 20. And there's going to be some rounding error here because we rounded off these values, but it'll get us pretty close. So what we can do now is we can now write the equations for I of t and a of t. And we'll go ahead and do that next. Give ourselves a little more space here. So we know that from the diagonalization vector decomposition theorem that we can write x sub t in vector equation form by taking k1 lambda 1 to the t times v1 plus k2 lambda 2 to the t v2. And so we recall that xt just contains our infants at time t and our adults at time t. And k1 is 25.53. Lambda 1 is 1.79. And that's multiplied by v1, which is the vector 1.12 and 1. That's this guy here. Plus our k2, which is 4.47, times lambda 2 to the t, which is negative 1.04. So we got to be careful here. We'll write negative 1.04. That's all to the t power. We didn't really even need the parentheses here because this is a positive value, but here with this negative, we just want to make sure it's negative 1.04 to the t, because that's our value of lambda. v2 is the vector here, which is negative 1.921. And then when we do all sorts of multiplications here, we get that I sub t, is equal to, when we multiply 25.53 and 1.12, we get 28.59. And that's going to be times 1.79 to the t. Just for consistency, I'll put my t above the parenthesis there. And that's going to be minus, because I'll have 4.47 times negative 1.92, which is negative 8.58 times negative 1.04 to the t power. And a sub t, if I do the same thing, well, these just multiply ones, so I'll have 25.53 times 1.79 to the t. And this will be plus 4.47 times negative 1.04 to the t. So one thing that we should notice already is that as t approaches infinity, the term that has the largest base is going to be dominant, right? Now we're not saying that these terms go to 0, but negative 1.04t will be negligible in comparison to 1.79t to the t for very large powers. So we're going to say that this is negligible. We're going to say that this is also negligible. And so over time, we see that the populations are going to grow by a factor of 1.79. So there's going to be a 79% growth rate. And there's our dominant eigenvalue right there. So what's going to happen over time is this vector, this initial state vector, 2030, is going to point in the direction of the eigenvector 1.12, comma 1, and we can actually take a look at to see that this is going to be an exponentially growing function by producing graphs of I of t and a of t using appropriate technology. Now I've already got the graph here for the two populations. So down here you can see I have infants at time t and adults at time t, those equations that entered in. Just notice that I have negative 1.04 all to the power of x. And then here I produce tables, and I'll show you why I had to create tables in a second. But it has to do with taking a negative number and raising it to fractional powers, because sometimes, like if this becomes x is 1/2, the square root of a negative number is undefined, or is not real, and so we can't do it for really many of the non-integer powers. So as time progresses, and we see that the infants are the green dots and the adults are the purple dots, and we can see that the adults are growing exponentially. The infant population is growing exponentially. And actually, we'll be able to see that the growth factor is about 1.79 or 179%. So we get all of the population from the previous time unit, but about 79% more. So let me come over to Desmos and just show you how this graph looks. Now, if I don't graph these and I put these equations in, we're not going to get a very pleasing result. Nothing gets graphed. I already know that my initial populations are 20 and 30, but I don't see anything down here. So the issue is the negative powers. That is, the negative bases raised to powers that are potentially fractions. So again, fractions can be square roots and stuff like that, and it's not always defined. So what I did here is I just put in a table, and once you have these two functions defined, I of x and a of x, here you can enter x values, and over in this column I will call this a of x1, because the values that I enter in this column will be my x1s. And then here I want I of, I guess we can do this in opposite order, I of x1 and a of x1. And now I'll start putting in some values here, and you'll see those points start to get generated as we move along. And oops, we'll take this guy out. And then 4 and 5 and 6. And so we can see that these populations are getting bigger and bigger. Now, one of the things that I want us to notice is that if you look at the growth rate from 535 to 929, that gap is getting much larger. And in fact, if I take if I compare, let me insert another expression here. If I compare I of, let's say, 15, and I divide it by I of 14, you can already see that 99,104 to grow to 177,438 represents a growth. It almost doubled. It was about 179% of its previous value. And also, if I look at a of 15 divided by I of 14, now that's not quite at the 179% yet, but if I start to make these bigger components in time, like I of 100 divided by I of 99, you can see there's our factor of 1.79, and if I do oh, you know what? I divided the wrong values here. This should have been a of 14, and it's there, 1.79. So the growth rate, that first term in these two expressions, is taking over rapidly. This second term rapidly becomes negligible. Now, if I compared and I should see that same thing here, if I compared the adult population at time 100 to time 99, I see a perfect 1.79 growth factor from time 99 to time 100. Also, if I look at the ratio of values for I of, say, 15 divided by a of 15, if I do I of 15 divided by a of 15, what I should notice is that ratio between those two values starts getting close to the ratio of I and a in my dominant, in my eigenvector. So here was our eigenvector. Its components were 1.12 and 1. And so if I come back here and I look at this, you can see this is 1.12. So the ratio of our components of our transformed vector after 15 multiplications by a pretty much is already pointing in the direction of the dominant eigenvector. And so the conclusion that we want to draw is, in the long run, at what rate is the population growing, and explain what the expected number of infants and adults will be per 100 adults. Will the elf population become overpopulated? So let's see what happens here. We've said that as t approaches infinity, this equation, this vector equation that we wrote up here, which is this guy, we're making the argument that as t approaches infinity, again, the second set of terms, this is essentially negligible, this whole thing, because that's going to revolve around taking a smaller base to a large power, and comparatively, this term right here is going to be dominant. And so this is going to be negligible. And so what this means that as t becomes really large, the ratio of infants to adults will be 1.12 to 1, which is, that's our eigenvector right there of our dominant eigenvalue. And each time you increase t by 1, you'll just get one more factor of 1.79. So here's what we can say. We could say that as t approaches infinity, the population will continue growing by 79% over each 5-year period. We don't want to say each year because every value increment of t represents a 5-year period. The ratio of infants to adults will be 1.12 to 1. So that ratio, no matter how much I continue to scale these two components, as long as they're scaled by the same factor, which they are, they're scaled by this coefficient here, the ratio will always be 1.12 over 1. So that's for one adult. There'll be 1.12 infants. So if I scale this up by 100 and scale the infants up by 100, that translates to, for 100 adults, this ratio is 112 infants to 100 adults. Now that's a perfect long-run analysis. Now, as you're probably noticing, it's really not entirely necessary, unless you want to graph the populations over time, to calculate these values of K1 and K2. This value isn't so much important as is which of these two vector equation terms is dominant. And we can basically just look at the eigenvalue and tell that right away. In fact, if we wanted to really make this problem short, we just had to look at the largest lambda and the corresponding eigenvector. And this will tell me that as t approaches infinity, the vector will grow by this factor, and the ratio of the two populations will be 1.12 to 1. So we're doing extra work, but we're performing some mathematics to be able to see it. However, it really just suffices to look at the lambda and the v corresponding to that dominant eigenvalue. So let's take a look at one more example. Here we're going to actually have 3 different states. And this is for a herd of American buffalo, or bison, which can be modeled by a stage matrix similar to that for spotted owls. This was a different example from somewhere else, so don't worry about the spotted owls. The females can be divided into calves up to 1-year-old, yearlings 1 to 2 years, and adults. So basically every year, calves are going to become yearlings. They can't stay calves because that's up to 1-year-old. And then every year, yearlings, the ones that survive, well, that's just from time 1 to 2, so at time 2 they become adults. Suppose an average of 42 female calves are born each year per 100 adult females. Only adults produce offspring. Each year, about 60% of the calves survive, 75% of the yearlings survive, and 95% of the adults survive. For k greater than or equal to 0, let x sub k be the state vector that contains the calves, yearlings, and adults in that order, where the entries in xk are the number of females in each life stage at year k. So we're not modeling adults, we're just modeling female bison. And so let's start off by building a state transition diagram for this. As usual, we're going to set up our states, which in this case we have 3 of them. So we'll have the calves at time k plus 1, the yearlings at time k plus 1, and the adults at time k plus 1. And so we know that each year about 60% of calves survived and they become yearlings. 75% of the yearlings survive, so they're going to become adults. Oh, and 60% of the calves at time k will become yearlings at time k plus 1. 75% of the yearlings at time k will become adults at time k plus 1. 95% of the adults survive, so that tells us that 95% of the adults at time k remain adults at time k plus 1. And if we really wanted to, we don't have to do this here, but if 60% of the calves survive, that means 40% of them do not, and 75% of the yearlings survive, so 25% do not. And same thing here, but this is going to be 5% of the adults at time K do not survive. So we don't really need these pinkish vectors at all. Those are just telling us that some of these animals bison are leaving the three states. So if we wanted to start a fourth bucket, we could say deceased, but that's not necessary. We don't want to keep track of those. We want to keep track of the living population. And also, we're told that 42 female calves are born each year per 100 adult females. So like our last problem, that means only the adults are going to contribute back to the calves. Now you can imagine that if we didn't have this arrow and there were no bison being born, eventually all the calves would become yearlings, which would all become adults, and then progressively those adults would die off at 5% a year. But we are getting 42, this is 42 per 100, so that means 42 calves per 100 adults. And we need to multiply that by how many adults we have at time K. So if we had 100 adults, that means we would get 42 new calves. And so we can just write this as, and remember, this is in the units of this are adults, so the adults would cancel out, and that tells us the number of new calves. And 42 divided by 100 is 0.42, so we can just say 0.42 A sub K. So now we're ready to build this model out, the recursive system of equations. And so we said that the number of calves at time K plus 1, well, none of the 0% of the calves at time K remain calves. 0% of the yearlings at time K become calves. But then we know that every adult will give birth to 0.42 offspring times the number of adults there are. We don't need to worry about this being fractional at this point. We're really just interested in investigating long-run behavior anyway. The number of yearlings at time K plus 1 will be the calves that survive, and so that number up here came out to be 60%. So the only way for new yearlings to become is for calves to survive, and that's going to be 60% of the calves at time K become yearlings at time K plus 1. None of the yearlings stay yearlings, they transition to adults, and none of the adults at time K become yearlings. The number of adults at time K plus 1, well, that's none of the calves can go straight to adults. They have to become yearlings first. We know that 75% of the yearlings at time K survive to become adults. And we also know that 95% of the adults at time K remain adults at time K. Now you can hopefully see what our coefficient matrix is going to be here. Short of writing it out, we're going to be able to see that the A matrix, in this case, the transition matrix, will be 0, 0, 0.42, 0.6, 0, 0, and 0.75, 0.95. So as you guessed it, we're going to now we're going to look at the eigenvalues and eigenvectors. I think we're going to skip over this question here. Find the eigenvalues and eigenvectors by using appropriate technology. Use the diagonalization vector decomposition theorem to provide equations for each of the three groups, calves, yearlings, and adults as a function of t. So no initial condition is given. And we note from the previous problem, our little observation, that really all we needed to look at was just the eigenvalue and eigenvector corresponding to the dominant one to determine what happens in the long run. So let's go ahead and write out x sub t. So for k1, k2, and k3 in this case, because we have 3 eigenvectors and 3 eigenvalues, we're just going to write out x sub t is going to equal k1 times lambda 1, which is 1.10 to the t power, times v1, which is 0.38, 0.21, and 1. Okay, now look at lambda 2 and lambda 3. We have an imaginary number in there, and I, if you recall, is equal to the square root of -1. If you remember when we found eigenvalues and eigenvectors, we had to solve a polynomial, and we solved quadratics. This is pertaining to a cubic, but it's possible to have non-real roots. So this is exactly what happened here, and so we might panic and say, well, how do we write that? You know, we could start to write plus k2 times the eigenvalue, which is -0.08 plus 0.41i times v2, right? And it's going to have its 3 components, and then do plus k3 times the third eigenvalue, which is -0.08 minus 0.41i times the eigenvector 1, 2, 3. But we're going to make the argument here that lambda 1 is dominant. But how do you do that? How do you determine that this is dominant when these guys contain imaginary components in them? So I'm going to state this without giving it much proof, because we would have to do some complex analysis here dealing with complex numbers. And you can see that even the 2 eigenvectors corresponding to the 2 non-real eigenvalues have i's in them as well. So we don't even want to write those down. It's going to get too messy. But here's the thing. You can say that a real eigenvalue is dominant to 2 complex eigenvalues as long as the magnitude of a complex number, where the way you find this, again, this is a result from complex analysis, so you don't need to worry about why this is right now, but the magnitude is just the square root of the component squared. So if that number is smaller than the largest real eigenvalue, then the real eigenvalue is dominant. And so you can see that A and B, when they get squared, they'll both be positive. So let's just verify this. So the magnitude of lambda 2 is going to be the square root of -0.08 quantity squared plus 0.41 squared. And if we do that in our calculator real quick, I didn't have this computed. Let me compute it real quick here. But you can tell that that number is going to be much smaller than 1, because we're taking the square root of decimal squared. And that comes out to about 0.42. And you can see that that is less than 1.10, which is what lambda 1 is. Lambda 3, its size, is going to be basically the same thing, -0.08 squared, plus -0.41 squared, which comes out to the same thing, which is still about 0.42, and that's also less than our dominant eigenvalue. Therefore, we can say that as t approaches infinity, so I'll write that down here, as t approaches infinity, this term here will become negligible, as will this k3 term here. That will also become negligible. And so we can say that x of t becomes approximately so as t approaches infinity, x of t is approximated by, I'll just say approximately equal to k1 times 1.10 to the t times the vector 0.38, 0.21, and 1. And so what that means is that first of all, this is telling us that this vector will ultimately point in the direction of v1, and every additional time unit, the components will grow by 10%. So this means that if this is the number of calves at time t, or I shouldn't say calves at time t, but the ratio of calves to yearlings to adults, I could say that for every 100 adults, I'll have 38 calves and 21 yearlings, and every year, all of those populations will grow by 10%. So as our summary concludes, we can say as t approaches infinity, any initial state vector, any realistic one anyway, that gets multiplied by a to the t will point in the direction of the eigenvector v1 of the dominant eigenvalue. So it'll point in this direction in 3-dimensional space. For each additional year thereafter, the state vector will grow by about 10%, which is the 1.10 growth factor. So for every 100 adults, the ratio will remain the same, because even if we multiply all of these by 1.10, or 1.10 to the 100th for that matter, the ratio of 0.38 to 0.21 to 1 will still be there. Because when you scale a vector, you don't change its slope, you just scale its components. So for each additional year thereafter, the state vector will grow by about 10%. For every 100 adults, we would expect 38 calves and 21 yearlings. And so that concludes us working with this. Again, all we really need to look at is the dominant eigenvalue and the corresponding eigenvector, and that will tell us what's going to happen in the long run.